So this is part 4 of the limit of a function note. First of all, we're going to look at some notation here. So we have the notation, the limit as x approaches a of some function is equal to L. And you read it as the limit of f at x as x approaches a is equal to L, where L is a number. So first we're going to consider the following piecewise function. So why is it called a piecewise function? Hopefully if you look at the graph you can see that it's in two parts here, or two pieces, and that's why it's called a piecewise function. And piecewise functions are defined differently. Usually we have our f at x and then a set bracket here, and it tells us that f at x is equal to different things at different times. So in our case we have f at x, our function is equal to x plus 2 when x is greater than or equal to 2. But it's equal to just plain old 1 every time when x is strictly less than 2. So it seems that 2 is an important number to consider in our graph here. Okay, so let's look at the x plus 2 portion of the function first. So when we have the restriction x is greater than or equal to, it says that we're allowed to equal 2. So if we were to put 2 into this function for x, we would have 2 plus 2, which is 4. So when x is 2, the value of our function is 4. We're also allowed to use any number greater than or equal to 2, so 2.1, 2.5, but 3 is an easy one to put in as well. So if we put 3 in here for x, we will get 3 plus 2, which is 5, which means that when x is 3, our y value is 5. When x is 4, our y value is 6. Which makes sense, okay, because if we look at x plus 2, we can see that that's a line with a slope of 1, okay, and a y-intercept of 2, but we don't actually have that y-intercept of 2 because x is not allowed to be 0 for this part of the function. So eventually, once we were convinced of it, we could draw in this branch of the function here. The second branch of the function is for x's that are less than 2, strictly less than 2. So though it can equal 2, it can equal 1.999 repeat. So it can get very, or infinitely close to 2, but not equal to. So what we tend to do is we pretend to sub 2 in, but we would have an open dot there since it's not actually allowed to equal 2. So if we put 2 in, we get back out 1. Anything we put in, we get back out 1 in this case. But I'm going to have this open dot when x is equal to 2. Then I'm allowed to put anything less than 2 in. If I put 1 in, I get 1, 0 in, I get 1, because this is a constant function, f at x equals 1. So no matter what x is, y or f at x is always 1, which gives us our second branch of our function. Okay, why is it a function? If you remember back from grade 11, it passes the vertical line test, which says for any value of x, there's only one corresponding y value. So this would be the only place we would be worried, which would be at 2, okay? But we can see this open hole does not signify a point on the graph, or on the function, whereas this closed dot does. So even at 2, we only have one corresponding y value. So this is a function, okay? If we look at what a is asking, we've got the limit as x approaches 2 with this little negative sign here. And what we really say to ourselves is that's the limit as x approaches 2 from the left. So limit as x approaches 2 from the left only here. So let's think about that. So let's think about x approaching 2 from the left. So as I approach 2 from the left along the x-axis, what's my curve actually doing? So my curve, as x is approaching 2 from the left, I'm on this branch, I'm approaching the value 1, okay? So I would say the limit as x approaches 2 from the left of that function is equal to 1. Now it's asking me, this limit as x approaches 2 with a little plus sign here is asking for the limit as x approaches 2 from the right. That's how you would read that in your head. The limit as x approaches 2 from the right. So here's x approaching 2 from the right. Along the x-axis, we're approaching 2. What is our curve doing at the same time? So we would be on this branch of the curve. If x was approaching 2 from the right, these would be our corresponding f at x's, and they are getting closer and closer to this value here, which is 1, 2, 3, 4. So the limit as x approaches 2 from the right is 4. Okay? And then it asks, what's just the plain limit as x approaches 2 of this function? Well, as we approach 2 from the left, we get 1. As we approach 2 from the right, we get 4. It's kind of like that sequence 1, negative 1, 1, negative 1. We don't have a consistent answer here. As we approach 2 from the left, it's different than approaching 2 from the right. So we would say the limit as x approaches 2 of f at x does not exist, because the limit from the left and the limit from the right are not the same. Which leads us to our big idea here, and that is, for a limit to exist, the limit from the left must equal the limit from the right. Or we can write that in mathematical terms. So this says the limit as x approaches a of some function is equal to a limit L if the limit as x approaches a from the left of the function is equal to the limit as x approaches a from the right of the function is equal to that same number in both cases, which is the limit. Otherwise, the limit as x approaches a of f at x does not exist. So that is a very important idea when we talk about limits, especially graphically. And that's going to be the end of part 3.